Alright, so in this tutorial we're going to pick up where we left off discussing class the basic forces, the rules that govern how matter behaves. We talked in class how there is basically a limitless number of actions that occur in nature, and those actions can be reduced to 4 interactions. The 2 most important interactions being attraction and repulsion. Alright, so let me try to give you a simple example. Let's say swinging a baseball bat, hitting a ball. When the ball and the bat meet, right, they both move as a result. That's repulsion. They pushed off of each other. Okay? Similarly, if you grab somebody and pull them towards you, that's an attraction. If you smack your hand on a desk, okay, your hand stops at the desk because of repulsive force between the two. It's not because matter particles came into contact. There was a force field that was repelling them. So almost everything that you do, in fact, pretty much everything you do is a result of an attraction or repulsion. Okay? Decays and annihilation are only at the nuclear level. So if you come across something that is everyday normal, you can be pretty darn sure that it's going to be a decay. Okay, so now what we want to do is talk about the various forces that give rise to these interactions. Now, we could also try to come up with a wide variety of forces like friction, drag, buoyancy, a hit, a push, gravity, stuff like that. So there's maybe not limitless number of forces, but there's quite a few out there. And like the actions, they can be reduced to a few fundamental, and that word fundamental is very, very important. It cannot be broken down into something simpler. So we got to learn what these fundamental forces are and then how they're communicated. And the weird thing is that they're communicated by what are called force carrier particles. It's an abstract concept, but we'll talk more about that in class. So let's name the forces right now, and I'll give you some information. And then what we really want to focus on about the forces is how they're used to hold things together in nature. Okay, well, let's start with the force we're probably most familiar with, and that is gravity. Gravity is a fundamental force. Okay, it is a force that's very important in our lives, but believe it or not, it's not the most important of the fundamental forces. Next question we can ask about is, well, where does gravity act? Over what range? And then what strength does it have? So its range is infinity. In other words, gravity acts near you and it acts way, way, way far away. It just happens to get weaker with distance. And its strength relative to the other forces is the weakest by far, which is kind of ironic because gravity is so dominant in the universe. But ounce for ounce, it is an extremely weak force. Now, of the 4 interactions, what does gravity do to objects? It always attracts. Okay, gravity does not repel, does not cause annihilation, does not cause decay. So I'll come to the last 2 columns later. All right. The next force is probably the most important force for our lives. It is responsible for all of biology, all of chemistry. It dictates pretty much everything you do. Most people just don't realize it. And it is called the electromagnetic force. Okay, and I'm just going to call it EM for short, because electromagnetic is a long word, and we don't want to have to write that out all the time. Okay, so same question before. What's its range? Electromagnetic, like gravity, acts over infinity. Okay, so it's strong when it's nearby, it's weaker when it's far away, and in terms of strength, it is fairly strong. It's second strongest. So it's much, much stronger than gravity. All right. Now, what kind of interaction do we get from electromagnetism? Well, like gravity, we get attraction. But we can also get repulsion. You've seen magnets repel each other. We'll talk about charged objects repelling each other, so you can get one or the other. But you don't get annihilation or decay. Okay, so those are the 2 most familiar to us. All right, in our lives, I'd say this is 90% of our lives, and maybe this is 10% of our lives. But there are 2 other forces that exist, and we want to be aware of them. It's just that they don't come up in everyday life. Right? So I'm going to name them both right now. One is called the strong nuclear, and the other is called the weak nuclear. So not very creative names, but they kind of tell you something about them. Nuclear. Okay, so in terms of range, the strong only acts at nuclear levels. In other words, the The strong nuclear force only acts over the distance of the nucleus, which is extremely tiny. It does not reach out to the everyday world. That's why it's not an important part of our lives. Okay? And it is the strongest of all the forces, hence its name. The weak nuclear force acts over nuclear levels as well, or the nucleus. And it is the third strongest, or the second or weakest. All right? It's stronger than gravity, but weaker than the other forces. And in terms of interactions, strong nuclear does attract and it repels. And the weak nuclear, notice we haven't hit two interactions yet. The weak nuclear is responsible for, more than anything, decays and annihilations. Okay, I'm just going to abbreviate that as annihil. Okay, so we've covered four important forces, the four fundamental forces, where they act over, what they do. Now, what kind of science arises because of these? All right, you might say, these dictate. What do they dictate? Well, gravity dictates more than anything, astronomy. Everything we see in astronomy, or many things in astronomy, are due to gravity, as well as some other forces. All right, to a lesser extent, it's part of Earth science. Okay? The electromagnetic force is responsible for, I mentioned this earlier, almost all of biology, almost all of chemistry. Okay, certainly some earth science, because a lot of earth science is chemistry and biological based. The strong nuclear force, what kind of science arises from that? Well, maybe nuclear physics. Okay, and then the weak force is really more than anything particle physics. I'm not going to hold you to that, but just kind of give you an idea of how these forces dictate major branches of science. Alrighty, the last thing in this is how do you communicate gravity? How does one communicate electromagnetism, etc.? So there are distinct particles that you may remember seeing on our chart that are responsible for conveying this. And I'll talk about how they work in class. All right, so I'm going to start with the electromagnetic, and I'll come back to gravity last. So the electromagnetic force is governed by something we might be familiar with, something called the photon. Okay, photon is usually associated with light and is given a symbol like that. It's like a Greek letter gamma. Okay, so when you see light bouncing back and forth between objects, that is a manifestation of the electromagnetic force at work. And light is a critical part of our lives, so electromagnetic force is a critical part of our lives. The strong nuclear force is mediated by something called a gluon. And a gluon kind of gives us an idea. It glues something together. We'll talk about what that is in a little bit. And then the weak nuclear force has these weird ones. We don't have to memorize them, but I'm going to tell you. There's a W plus, a W minus, and a Z naught. Okay, these weird particles called bosons. Okay, the point being of these three, they're very distinct particles from one another, have different properties. Photons can act over an infinite range. Gluons can only act over the size of a nucleus. All right, the last one for gravity is called the graviton. And I'm going to put a question mark next to it because we haven't discovered it yet. So we're not really sure if it exists, but a lot of our theories suggest that they should. Okay, so let's finish up. Perhaps the most important thing is how are these used? I'm sorry, there's a new one here. I added this here. There's another type of force out there that maybe I'll talk more about in class called the Higgs field. Okay, and it was fairly recently discovered and confirmed, even though the idea has been around for a few decades. And what's very special about the Higgs field is it gives particles mass. Okay, anytime you measure mass in a particle, it is because it is interacting with this thing called the Higgs field. Without the Higgs field, everything would be massless, and that's the significance. And the symbol for the particle is called the Higgs boson. Okay. Actually, the zero's up there. That's a big deal. Okay, now we can turn our attention to how do these forces affect our lives. Okay, so we're going to go to something a little bit familiar to us, the structure, things that are structured in the universe. All the way from the tiniest thing like hadrons to the biggest thing, the universe. What holds it together? So it's got to be one of those forces. All right, so let's take the universe. I'm going to work our way back. What holds the universe together? more than anything, it's good old gravity. Gravity between galaxies and clusters and galaxies, etc., is what gives it some structure. Now, we take a galaxy, which is a bunch of stars. What holds all the stars together into that unit called the galaxy? Well, that's gravity as well. And what holds our solar system together? What holds the planets going around orbits? We've talked about that. That's gravity as well. So we see that gravity is over distances of astronomical distances. Now, what holds a star together? A star is a big giant ball of gas. What keeps the gas formed in a spherical shape as opposed to just diffusing out? That's gravity. Now, when you start getting to planets, what holds the planets together? To a certain extent, that's gravity, and it's also the electromagnetic force. So that plays a role. The electromagnetic force will give rise to solids versus liquids versus gases, and gravity holds all the mass together. So notice there's a pattern to this. Now we get into everyday stuff. What holds me together, what holds a board together, what holds a car together. It is not gravity, it is the electromagnetic force. It is the attractions amongst molecules to each other due to electrons and to a lesser extent their nucleus. What holds a molecule together, like H2O? What holds the two H's together and the O together to make those covalent bonds or even ionic bonds and salt in that? That's the electromagnetic force. What holds an atom together? What keeps the electron going around the nucleus? Think about that. You should know it. That is also the electromagnetic force. So we see that the electromagnetic force is responsible for the stuff that makes up everything in our lives. That's why it's so important to us. Now we have the nucleus. What holds it together? The nucleus has lots of protons and neutrons crammed in a tiny little space. Those protons want to repel each other by the EM force, so there needs to be a stronger force to overcome that attracts it, and you can probably take a guess that this is a strong force. So the strong nuclear force acts over nuclear distances, and one of its jobs, if you will, is to hold the nucleus together. And then what holds a hadron together? Remember, a hadron is a quark, and a quark all bound together in a tight little space. So you need a pretty strong force to hold them together, and you'd be correct if you said it was the strong. Okay, so we see a pattern here as we go from the smallest to the largest, which force is taken over. And if you'll notice, what force isn't showing up? It's the weak force. So the weak force really doesn't hold structures together. Instead, it is primarily responsible for matter breaking down or annihilating right? Or changing flavor. And changing flavor is a way of saying changing its identity. Okay, so what I want you to do on your own, when you come to class, to see if you do it, and I'll do a few together, is given the following situations, which of the four forces are responsible for them. You have the chart above. It should be pretty straightforward. Okay, so the first one holds up and down quarks together to make a proton and a neutron. As soon as I see these, I see that they're at what level? That's correct, the nuclear level. So that's going to be the strong force. Okay, what keeps all stars, black holes, and gas clouds bound in our galaxy so they don't stray off? Of course, that's gravity. What allows a muon to decay into an electron and two neutrinos? The key word is decay. And so if we go back up there, we saw that that's what the weak force does. Actually, on the other side of the page, so the weak does that. What keeps protons tightly packed in the nucleus of an atom? Again, there's nucleus. So it's got to be something over the nuclear level. That's the strong force. All right, let's do one more, and then I'll let you do the rest, and we'll get the answers in class. What prevents your butt from falling through the chair you're sitting on? Okay, so your butt and your chair are well beyond the nuclear scale, so it can't be the stronger or weak force. So it's either gravity or it's the electromagnetic force. And so there's a repulsion between your body and the chair. And at what level is it? Is it at an astronomical level? No, it's at an everyday level. So that tells you that that's electromagnetic repulsion between the molecules of your body and the chair. Okay, so try the other four. We'll talk about them and do a little bit more in class.